Next topic area, P9, forces and their effects. And we've got an athlete runs a 100-metre race. So, whoops, I've gone too far ahead here. So I've got a distance. It uses an average force of 120 newtons, perfect. And then it takes them 11 seconds. And it says, what's the power of the athlete? And we've got a clue here. It's telling us use fat wobbly dinosaurs first, then use pet second. So if I just get those formula triangles ready, so we're going to have, try and make this a bit neater. So we've got fat wobbly dinosaurs, and then we're going to use that to work out the work. And we've said already, work is the same as energy. And then we're going to use that. So it's work out the work and then work out the power using the W changes to the E. Here we go then. So work equals force times distance. Perfect. So our force is 120. The distance they went was a 100-metre race. Times that together. Gives us an answer of 12,000 joules. Perfect. Now we want that value. Work is the same as energy. So we're going to use this value. That's going to drop down to the next formula. You see this is a tricky question. So the next part, power equals energy over time. Bring down the work, which is the energy, 12,000. Divide by the 11.6 that it took them to run the race. And we've got the power is 1,034 watts. And you see you've got watts again in terms of a unit. On to the next part. We've got, is this moment in equilibrium? You must show you're working out within your answer. So we know the principle of moments. A system is in equilibrium if the clockwise moment is equal to the anti-clockwise moment. And you need to know that definition. We're going to show working out. So if the clockwise, the right-hand side is equal to the left-hand side, it is in equilibrium. So we've got our formula triangle to help us with this. Remember, all of these are in your formula book at the back. It's being able to rearrange them, which you're good at. So we've got fat, moody dinosaurs. So you've got wobbly ones and you've got moody ones. So the moment equals the force times distance. So we're going to do that for that side. The force is 21 times 1.25. And we've got our turning moment of 26.25. So just like in maths, here's my moment. And ultimately I've got a force, newtons, multiplied by a distance, meters. And in just the same way as A times B equals AB, it's the same with those units. So our unit is Newton meters. So we have done the anti-clockwise moment. Now let's do the clockwise moment. So 7.5 times 3.5, 26.25, Oh my God, they're the same. Then you got to write your sentence. Yes, it is in equilibrium as the clockwise moment is equal to the anti-clockwise turning moment. Done. Next one is gears. I always say if they give you a worded one without a picture, put a picture. Usually there's a picture with all of these. We've got a 12-tooth gear is rotated. So I'm just going to draw a picture. There's my 12 teeth. Oh, this pen's having a wobbly today. Come on, pen. So there's my 12-tooth gear and it's being turned clockwise. And remember, we've learned that machines, they can change the direction or the magnitude of a force. Now we're going to attach it to a 20-tooth gear. So the 12 is being turned. So I'm just going to draw myself a bigger one. 20 teeth. Well, what I do know is if that one goes clockwise, this is going to end up going anti-clockwise. And then it said, what direction will it turn and what will its rotational time period? So our first job, find the gear ratio, 12 to 20. Next one, turn it into a unitary ratio. So take the small number and put that into, or divide the 20 by the small number. Now we've got the unitary ratio. So the gear ratio is here 1.16. And I've taught you, well, if I go from a little gear to a bigger gear, this is going to have less rotational period. And I'm going to be careful not to say it rotates slower, because in this point here, they're actually rotating at the same speed, but it's just going to have less rotations. So now I know that 20 tooth is less rotations. Well, I've got my number 1.66, and clearly I'm going to have to divide the rotations by it to make a smaller number. So 20 divided by 1.666 equals 12 RPM, and it's going to go anti-clockwise. The next one is the company wants to add, and I'll change the, the company wants to add another gear that provides a clockwise turning moment with double the rotational period. And we've looked, well, if I add another gear, so let's just add one here, and I'll put a mystery thing there. Well, we know that any of the gears in the middle don't matter. So that's now, but it will be useful in terms of making us get that one clockwise. So I've added a gear on the end here, and that's going clockwise, anti-clockwise, clockwise, perfect. Then the next one is I want it to have double the rotational period. So I've then got to decide, do I want a smaller gear or a larger gear? Okay, now I'm going to draw my little picture. Well, for this one to rotate more often, I need a smaller gear. I want it to go twice as fast, so it needs to be half the number of teeth. So that's going to have to be 6 teeth. That's that one done. So add a third gear next to the 20. I don't want it next to the 12 because otherwise the 12 is in the middle. I don't want that, because the only ones in terms of gears that we look at is we look at the driven. What's up with my pen? I'm going to have to fix this. And we look at the very last gear. Okay. Add a third gear next to the 20, and it needs half of the teeth. Now I've got another one. A balance beam is in equilibrium. What's the distance required to make the beam balance? You can see the answers there already, pretty much. Not sorted my animations out properly. Split it down the middle. There's the pivot, and we've got our fat, moody dinosaurs again. And then it's just a bit of math. So we're going to work out the side where we've got 2 bits of information to work out the bit of information we don't want. So we want to find out what's the distance over there. So our first job, find the turning moment on this side, move that across to this side, and then use that to find the distance. So here we go. You're very good at these in class, so I'm hoping you nail these questions. So turning moment equals force times distance, 12 times 2, 24 Newton meters. Now I'm going to move that number 24 across. You can see it's moved across already. So the distance equals the moment divided by the force. Well, that's the 24 that we've moved across. And just show it being moved across. So that's my 24, divide by my force 3, and I've worked out that the distance equals 8 meters. And the last one, state the principle of moments. A system with a pivot is in equilibrium when the clockwise moment is equal to the anti-clockwise moment. And you can see I've just put a bunch of extra words in it from when we revised it. So a system with a pivot is in equilibrium when the clockwise is equal to the anti-clockwise. Please make sure you include the word moment. All right. And then is that the end of that bit? It certainly is. That's that bit done.